I'm giving 2 slides, and then I'm going to let Munib talk. Okay, so we're talking about more kind of generic trajectory analysis, not just MSM analysis, but doing everything, and mixing and matching, and kind of making up your analysis as you go. Not like making it arbitrary, but doing what you need to do. Okay, so I'm going to give just 2 slides on the kind of overview of kind of our vision of how this works, and then Munib's going to give a demo and a kind of tutorial, and we're going to all do it together. Okay, so the overview is that as data, molecular dynamics data is just data, and data science is bigger than MD. Okay, so a lot of fields are having the same challenges that we do in, I've got terabytes of data, how do I analyze it? How do I do machine learning or clustering or whatever? There's nothing specific, well, there are a couple things specific about molecular dynamics data, but classification and regression and time series analysis and dimensionality reduction, the kind of complex parts are not specific to MD, okay? So siloed software for analyzing MD just doesn't make sense in 2014. So a single software package that says, I'm going to read trajectory data but also be a statistics package, what you're going to get is a bad statistics package, basically, right? What we want to do is link up communities and use sort of industry standard tools and connect our data to that. Okay, so that's what MD-Traj is, and MSM Builder is one of the applications that uses MD-Traj. So things like RMSD or whatever that are not specific to Markov models, but are specific just to molecular dynamics and measuring distances. Okay, so there are really 2 big communities in software for data. One is Python now, and one is R. R is a special, I mean, there's also like SPSS and stuff in social sciences, but those aren't as good for big data sets. So R is a basically special purpose statistical language, and Python is a do everything language with really good packages for machine learning statistics, performant data analysis. So the goal of MD-Traj and the kind of tools we're going to be presenting is not to make plots or do PCA. It's to bring your data in 1 line or 2 lines into a format so that you can do all this analysis and mix and match. So it does a couple things really well. One is read MD data in any format that you have, not just ones that OpenMM will write. And so obviously you can convert between them or whatever. And the other is compute geometric observables that you would want to use as input to some other method that really are specific to molecular simulations, like RMSD or hydrogen bonds or something. And both of those things, it tries to do not too many things and do them pretty well. So it tries to read everything and compute these geometric observables really, really fast. So we wrote all this stuff up extremely low level, but then expose it with a really convenient Python API. So that kind of, So I'll just let Munib kind of show off how this stuff works. And basically, it's kind of showing how you can build your own analysis in, say, IPython, not in Bash. That's kind of the 2014 way.
Thanks, Robert, for the introduction. And the idea is that I'm coming in from a applications background, and so most of the time I will be running all these long trajectories with basically no way of analyzing them. So if you have ever used any MD package in the past, like every set of software like GrowMax or Amber or all these, they have like their own built-in stuff that you can do for data analysis of their own trajectories, but there's nothing that can do it all at once and all within a single Python framework. And the idea behind MD-Traj is that you don't have to be you don't have to basically use, for example, the GROMACS is really disgusting bash format to get maybe like the 10th dihedral out. You can do it directly using an in-browser and plot it automatically into an image that is like publication ready as quickly as possible. And the reason why you want to do it is basically once you build these models, once you have these states, once you have these MSMs, how do you understand what these states mean? So in the last tutorial, when Robert went over these phi-psi angles that alanine dipeptide decomposes into, how do you get those phi-psi angles for that particular trajectory? Or if you actually did I think this would be a good point to actually open up the IPython notebook for the MD-Traj tutorial. So can anybody just do that right now so that we can all sort of be on the same page and I can just start scrolling down. So basically, the start of the file has a bunch of helper information on who made MD-Traj, and it was basically Robert in the back there, and then Kyle, who is an alumni of the lab, and a lot of people on GitHub. And the idea is that you can go to either the md-traj.org website, or for pretty much getting an idea about what the capabilities of this package are. And so if you look on the side, you'll see how to get the code, what the examples are, what it can do, and then this is probably the most interesting thing for today, which we will be using a lot of, what kind of trajectory analysis it can do. And the idea is that the trajectories that you can give it don't have to be MSM trajectories. They can be pretty much any trajectory they can throw at it, be it from GROMACS, OpenMM, Amber, NAMD, Yasera, whatever. It doesn't really matter. So basically, and then there are some help features for IPython notebook. I don't know if you would need at this point, but if you guys sort of want to know what else IPython can do, I think these are pretty interesting links to go to. Some of them are actually pretty fun to play. I think there's one which allows you to make XKCD type of plots for all your data, so that's kind of interesting. So I'm going to actually basically work on a relatively big system, Ubiquitin. And if you guys actually did your homeworks last night for running a implicit solvent simulation of Ubiquitin, hopefully you actually saw the same things as these tutorials are going to show you. And I would encourage you to go back and load up that data and see if you actually see the same things in the Ubiquitin that you ran with what we have provided you as basically cross-validation and to convince yourself that these kind of tools work. So in case anybody needs some idea about what Ubiquitin is, it's a signaling protein that targets different misfolded proteins or anything, and other proteins that are going bad for degradation by the proteasome. And it's basically implicated in a lot of diseases, and nobody really knows how it works. How does it know which proteins to target? How does it know what to select for? How does the proteasome know? And so on and so forth. And so the MD simulations you want to figure out what kind of degrees of freedom these Ubiquitin has that enable it to select for certain proteins or enable it to sort of find its right target. So the system that we basically ran is this wild type system, which has okay, this is too big. This two-state model behavior. And what I'm basically showing is an overlay of two states. And what you can sort of see is that the system doesn't really change that much except for that loop at the N-terminus region. And it just sort of goes up and down. And the red and the orange are going to be the color scheme that we'll be following for the rest of the tutorial. So this is sort of like a biological motivation as to what we want to do is figure out what is causing that up and down motion eventually. And so what we can do is, let's just start by actually loading up these trajectories. So in order to do that, first you'll need a bunch of libraries. The first is MD-Traj, obviously. Then NumPy is used for a lot of array operations. And matplotlib and pylab in line is basically for plotting, so that we actually can see the time series of the trajectories as they evolve over time. Now we'll get to the actual trajectory analysis portion. So in the folder that was provided to you, you should have two XTC files, which is ubiquitin-traj-1.xtc with its topology file, which is ubiq-crystal.pdb. And basically, you can load a trajectory by just saying trajectory_1 equals md-traj.load. And the thing about with md-traj is that it will figure out if it's XTC or DCD or I don't know, whatever else formats it can actually, like any format it'll need to read, it'll just automatically figure that out and do it for you. So you don't have to tell it, oh, this is the format I'm going to provide you with. The idea is you basically just say, okay, load this trajectory and give me a object, which is traj_1, which has a lot of, which basically is the trajectory object that MD-Traj can work on, or that you can sort of query. So you can shift enter, and now it's basically loaded. And if you actually just write this traj_1 and press shift enter, what it'll tell you is that it's loaded this trajectory. It has 400 frames, 1,223 atoms, 75 residues, and it's stored at some location in some place, I don't know. But basically, it'll tell you how many atoms it has, how many residues it has, so you can do a quick check and as a sanity check and be sure that this is the trajectory that you actually want to query. So the thing is, though, that since this is basically corresponds to this red state, but now we need the data for the orange state as well. And that is stored in ubiq-traj-1-2.xtc. And so what I would like you guys to do now is to basically follow along and load, using a similar format, ubiq-traj-2 into a variable that's called traj_2. The topology is exactly the same file. And the idea is that you'll now have two trajectories loaded in memory, one that corresponds to the up state, one that corresponds to the down state. Oh, and in case this wasn't obvious, there are a lot of these, like the IPython notebook has a bunch of these cells where there are these markers that you need to fill in as you go along. So the thing won't work without you actually participating. Start by filling in how you would load the trajectories. Okay, so now let's figure out how many, basically how many frames, atoms, and residues traj_2 has. So in the next cell, just write traj_2 and just press shift enter. And so this is like a made up example, but basically I pulled equal number of frames from both the states. So there are 400 frames in both the up, the red state, and the down, orange state. And now, but you'll notice that the location here is now different, so it's actually not storing it in the same place, thankfully. And it's basically, it has the same number of residues as before and the same number of atoms. So one of the really nice things about MD-Traj is that you don't have to do analysis on trajectories or MSM states one at a time. You can actually add a bunch of these trajectories together because the plus symbol is overloaded. So if you just write combined trajectory is equal to traj1 plus traj2, it will basically concatenate those trajectories together. And it's really smart of figuring out, oh, if these are like of different sizes or if they are like different number of atoms or something, it'll just sort of throw an error and tell you can't add apples and oranges together. But it will basically just be able to figure that out, but you can actually add these trajectories together and have one long trajectory instead of having to do analysis on like a bunch of things at a time. Now, if you see, you basically have 800 frames, which is 400 and 400 together, but the number of atoms and the number of residues are the same. So now you basically have the entire thing in memory, and now you can start doing the actual data analysis. So let's take a look at, I think the first thing that pretty much any, like if you read any paper that is MD related is going to be they'll plot some kind of an RMSD of the system over time. And the idea is that you want to calculate, okay, let me find out what is changing over time. So I'll just take a look at the root mean square deviation. So this is basically the format for doing RMSD calculations. What it is doing is basically saying, okay, give me a target structure to align to, give me the target trajectory, a reference trajectory, the frame in the reference that you want to align to, and then we can figure, and then the atom indices to use for the RMSD calculation. And you can basically calculate the RMSD for the entire trajectory by just a single line of code. So this is where I think the power of Python and MD-Traj comes together. You calculate the RMSD, and you can color it, and you can plot it instantly and look at it. So again, the x-axis is time units, so it's 800. The y-axis is in nanometers, and it's basically saying that that this trajectory is pretty stable around 2.5 angstroms, or something like that, and it will do a lot of different things. And I think you can basically get publication quality figures pretty quickly out of IPython and without having to ever leave a browser while you're playing around with data. But the problem is that this seems like a lot of random noise right now, and it's not that surprising. If you go back and look at these PDBs, the only thing that's changing is this small region right here. And so what you can do is plot the RMSD of just the atoms in this particular sequence without having to calculate, oh, this entire region is just noise in your data. So the way you do that with MD-Traj is basically supplying it these atom indices file. But now what you need to do is you need to actually create an atom indices list. So we can start that by, if you go over here. Now, what you want to do is create a indices list between the atoms that, this is like basically if you look at the structure, you'll figure this out, but the atom indices that correspond to the loop are 113 to 201, I'm sorry, 202. And what you can do is you can basically change this indices list to that range and then print it out to get an idea about and get a list of all the atoms that you want to use in your RMSD calculation. In case anybody didn't see this, the answer is right here. Basically, you need to give it the indices to use in the RMSD calculation. So what you can do is come over here and change this right now to 02. And add another line over here, which is this is equal to indices list. And okay. And now we can plot the loop RMSD. And I think this is hopefully a bit more clearer. What you can see is this one state where the loop is up. And since we are aligning to the initial structure, which is this red state, that has a lower RMSD. And then as it moves down, the RMSD increases and stays stable in that region. And that is sort of a quantitative way of showing that the loop is changing over time. Instead of just looking at a movie and being like, yes, it's changing, you can quantify that using this RMSD metric. But that's like basically, it's showing us a lot, but let's go one more. What you can sort of, I think what I would argue is that you can quantify this loop movement a bit more if you can plot the dihedrals that correspond to this region and that region right here. So as the loop goes up and down, there are dihedrals in the start of at the hinge region that will quantify that loop motion a bit more. And those will correspond to the phi and the psi dihedral. And I think this is basically what you want is if you want to calculate, let's say, the phi dihedral for the entire trajectory, you just give it a single command, which is md-traj.compute phi combined trajectory. And it will give you two outputs. One is going to be the indices list, which is just the phi, which is just the atom indices that correspond to the phi dihedrals in the system. And there would be, for example, I think there are 77 residues, so this should be 76 times 4. And then it will also give you the phi dihedral, which is going to be a m by n matrix, where m is the time points, which is 800 in our case, and n is the number of phi dihedrals, which I think should be 74. Yeah, sorry, I'm sorry, 74. And so what you can do is you can basically plot any dihedral that you want in this entire matrix. And this calculation is extremely fast, so I wouldn't worry. You can throw very large trajectories at it, and we'll do it very quickly. Now, let's say you want to plot the fourth dihedral. So what you can do is you can say, okay, plot phi dihedral. I want all the rows. So that means I want all the time points, but I only want the fourth column. And that's basically only going to plot the fourth dihedral there. And I want it in the color red, but we can change that to, I don't know, green or something like that. The answer is in radians, so be careful about that. You might want to do a unit conversion at some point, and there are methods to do it pretty quickly, or you can just add a single multiplicative factor of 57 or something like that, and that should be fine either way. And you plot it, and what you'll see is, over time, I think the 400-point mark is what you want to look at. It has one motion in one state, and then as it goes down, the dihedral changes, and you can quantify that by just looking at how this dihedral is evolving. Okay? I think there is enough time to do maybe one last small practice, and what I would like you guys to do now is plot these series of dihedrals. So the fifth dihedral, the 12th, so the fifth and the 12th phi dihedral. And so that would be the one basically corresponding to the 12th dihedral would be the one on the hinge on the other side. And so you can quantify the hinge motion by looking at either one end or the other end. It doesn't really matter. And these are just the projections that you use to sort of quantify how much the loop is moving up or down as it goes through this conformational landscape. So if you would like, I think you can basically go back to md-traj.org. That's here. And then go to trajectory analysis and play around with pretty much any of these different order parameter calculations. And I think they go from calculating RMSD in a bunch of different ways, calculating the hydrogen bonding pattern in a trajectory, which can be pretty useful, surface area, radius of gyration, to figure out how compact a protein becomes over time, which might be useful if you're doing some kind of a folding simulation. You can compute any arbitrary distances. So if you're doing some kind of a docking or some kind of a drug binding, you can look at contacts between the drug and the target compound. You can actually compute contacts. So if you have some kind of a conformational change in your system, you can look at how the contacts are evolving over time. I already went over the dihedrals, but angles, being able to calculate pretty much any arbitrary angle by giving it just three atom indices can allow you to quantify any motion that you can possibly think of. For example, if a protein is like closing or opening up, you can calculate that angle by just giving it the 3 points that you think would correspond to that order parameter. And basically, it can do phi, psi, chi1, chi2, chi3, chi4, and any of these different, like an omega as well. And the idea is that I think Robert basically optimized and worked on this a lot. So a lot of the different, like I know for a fact that, for example, the GROMACS GChi tutorial, GChi has a problem with different atom names. And if you give it the wrong atom name type, it actually has a problem in being able to calculate those dihedrals properly. And so a lot of that was actually ironed out in this. And the whole point is that you can do it in browser without having to ever leave the safety of Python. And I think one of the better things that's coming out recently, which is I think Kyle's work, is calculating NMR observables. So in theory, you could predict what the NMR observable using this program called Chemical Shift X2. And I believe it still requires that you have Shift X2 installed and then add it to some kind of an environment. But you can basically plot and look at, okay, if this is what I think the activation trajectory is, can I basically correspond that to some kind of an NMR observable directly without having to do a lot of work by just exporting that trajectory into some other format that the Shift X2 can read and then figuring out how to run Shift X2 and all that. This will sort of handle it for you. And I think it can do Sparta Plus as well now. So whatever your favorite NMR prediction package is, you can use that to sort of predict what the NMR observable is going to be. Okay, so with that, I think that's all for me.